Hello, my good friends. Hello, my RF and microwave circuit and system design professionals. I greet you again. This is Dr. Mohamed Nezami. I'm continuing today with the second video in the series on the 5G, both sub-6 gigahertz and millimeter wave RF transceiver design. I'm mostly interested in looking at the small cell, picocell, and even macro cell architecture, where I zone in on the RF transceiver. And in the past video, and you can check my video down there, I have covered the fundamentals of 5G RF transceivers. And so today we're going to continue more. We're going to look at the both the sub-6G and the millimeter wave transceivers, okay? Now, if you, just so that I could remind you again, I operate out of Jerash, Jordan. I have a HFSS design and modeling training that I hold every other month. It's in this place here. Well, this is the past one, but reach out to me at this email here, or you can call me. My phone will be provided shortly, or message me through the telephone apps like WhatsApp and Telegram. I have also other trainings, one on the use of the Pathwave, ADS, and RF Pro, and Momentum. Then I also have one training on the cadence layout and schematics as well. So we have the full entire tools for microwave and RF board designs, board level designs. So like I told you a minute ago, I have also another training, two trainings, one on the Pathwave ADS system and one on the Pathwave SystemVue. And what the SystemVue one, I cover basically the concepts that we did in the videos. You can refer to my videos here. I have covered design of LMBs and block-up converters for SATCOMs, KU band, also the front end for the RF front end antenna and RF front end for the Inmarsat system. And now we're covering the 5G transceivers using SystemVue as well. So I give two of these trainings. If you have a need for these trainings for your organization, especially operations in the Gulf countries like Saudi, United Arab Emirates, Egypt, Turkey, I could come to your site and deliver these trainings, or you could come to me and we can hold these trainings. I could customize them based on your needs. I also have, I offer my RF level, board level circuit designs, where I take your concept and realize it in a board, schematics, Gerber files, bill of material, and the artwork as well. So my rate is very reasonable. I'm running right now a special rate at this rate here. So reach out to me with this email, and I have clients that I have worked with in North America and in Europe and Asia. So you could reach out to me if you have a design that you want to outsource. I will work with you, and we very efficiently and very rapidly delivering stuff. Thank you. Now, let's get back to 5G. So in the last session, in the last video that you can go down here and view that video, I recommend that you watch that video before you come into this video. We have covered that 5G or 6G, 6G is basically built on 5G. It's the same hardware with an extension of capabilities. So we know that we have two distinct regions. Okay, the one region which we call sub-6 gigahertz, okay, which is these ends in here, new 77, new 78, new 79. All these designated bands are around these areas. With very popular band is the 3.3 to 3.8. Okay, we also have down below in the 2.5 to 2.7, which is the old MMDS that I used to work in the 80s and 90s circuits for that back in the US. So we have that as well, but mainly I'm going to cover stuff that has to do with these bands here. So then we have the millimeter wave bands. Okay, these starts out from 257 all the way to 261, and these are usually right here. The most popular are the ones that are classically called KA bands, 24 to say 32 or 24 to 29, I would say. Okay. Also 27 to 28 as well. So, okay. Now, the difference between these systems is that the upper frequencies here, we have the standard requires that you do beamforming with MIMO. These ones here that you do MIMO. So the intention in here is the array antennas are intended for capacity increase, where these one here, the use of beamforming is basically intended to optimize the coverage, so you can actually zoom in on users and increase the signal to noise ratio, so you can deliver higher data rates. Where this one here, you could the use of multiple antennas is mainly for spatial multiplexings, where you can double up or quadruple up the data rate, because you're using basically orthogonal beams or spatially separated beams. All right, so in the last session, we have concluded that from a hardware point of view, to build receivers and transmitters for these two bands, the sub-6 gigahertz bands, we do not need any frequency translations. We can go directly from bits to antennas using high-speed ADDs and DACs, okay? And we know that these nowadays are available with the DAC sampling rate up to 12 gigahertz, and then 12 gigasamples per second. And then we have ADDs that are available all the way up to like 8 gigasamples per second, even more some, but commercially from various sources like E2V, Analog Devices, Texas Instruments, all of those guys deliver these. Now, the millimeter wave, we do need a single frequency translation. So we can come in like on the receive side in here. If you're operating, say, between 24 to 29, you need to get down to sub-6 gigahertz, and then you just basically recycle a design from above here. So, and that's what I'm going to do in the demos that I'm going to demonstrate. So I'm going to demonstrate a multi-antenna, multi-input, multi-output array transceiver at the sub-6 gigahertz, and then what we will do is we will extend that so that with a single frequency translation to go up to Ka bands, these millimeter wave bands. Now now, even though I drew here receive path, but transmit path is exactly the same, just reverse the sample, the direction of this amplifier. So in that case, you'll be using DACs, filter out amplifiers, drive antennas. And then in this case, you would use DAC, filter it, and up convert it, and then filter, and then a power amplifier, just reverse that. So now let's look at the system level, the sub-6 gigahertz transceivers. Okay. Now we could, from last time, we also just revealed that we could have two options. We can go use off-the-shelf system on chip, packages like Xilinx out of SoC that has in it the baseband processing, all the signal processing portion, the modulator, demodulator, to build up these with included with internal DACs and ADDs included in the FPGA. Or we could use a discrete components from analog devices or from Texas Instruments. For instance, this one here from analog devices, it's a 4x4, 4 transmit, 4 receive chip. So meaning it has 4 DACs, 4 ADDs, okay? And what we do, we can build a sub-6 gigahertz RF transceiver for 5G based cell transmitter system using these chips. So now back to the FPGA, it's exactly the same. The only difference is that this one here, okay, is very much it doesn't have a lot of programmability like you would on an FPGA. On an FPGA, you have what we have in the discrete chips from these various semiconductor companies, where that includes the DACs, ADDs, and all the back-end signal processing, okay? Which the FPGA also includes that, but in addition, it includes capabilities of implementing various different functions other than the standard functions. You get the standard functions, which are the inverse Fourier transform on the transmit side, the FFT on the receive side, and then all the complex number processing that you would do to the signals and the uplink and then the downlink, the AGC, mixing, rotation, band chopping, carrier rotations, and so forth. And the same thing, you would have all these functions are included in here, including, of course, the power amplifier pre-distortion. That's where we feed the output of the PA and go back into a dedicated receive path for this, or we could multiplex the signal into this receiver so we can do linearization prior to going on air, okay? So so basically, these are TDD systems, time division duplexing. So meaning the transmit path and receive path are simultaneously working, and they're being multiplexed using a circular that isolates the transmit and receive paths, okay? Now, with this system here, typically, if you're operating, say, at 40 dBm, with the DACs in here, that, for instance, in this example that I captured from the Zinc app notes, you could go out with minus 18 dBm. This is a backed off signal due to the high peak to average ratio and including headroom for the pre-distorter. So you can go from minus 18 to 40. So that means you have about 60 dB of gain that you have to implement between the antenna and the DAC, including, of course, you go out and transition from balanced to unbalanced or single-ended. So that we're using a balance. All these components are off the shelf, and I will demo one modeling of a chain like this in the SystemVue Pathwave shortly or in the next session, okay? And the receive path, we usually go have about 40 to 50 dB of gain in this path here. So now typically the noise figure of these systems are a bit higher than usually would think of in terms of SATCOM communications, where usually you operate with sub 1 dB numbers or a little bit below 2 dB numbers on noise figure. In this case, we really have about 6 dB. So just primarily because we have a filter, we have a circulator, and we have an LNA that is in the sub-6 gigahertz. That's unlike the devices available for KE bands. Okay, so but that's good because we don't care anyway. We're not trying to receive a signal from above in the skies with a lot of distances. We're dealing with distances anywhere from 200 meters to a few kilometers. So signal levels are not like minus 1 120 dBm. They're up in the probably 60 dBm, 70 dBm, 80 dBm type. And that's why we wouldn't need that much of a signal to noise ratio. I mean, a noise figure. So again, to do the implementation, like for instance, in this case, this chip here has 4 transmitters, 4 receivers. The ADD is running at 4 gigasamples per second. The DAC is running at 12 gigasamples per second, okay? And so we could get out of here minus 10 dBm and transform it to any power level we want to provide the EIRP that is common for small cells or macro cells, like 60 dBm EIRP, 40 dBm EIRP, 50, 20, and so forth. Now, the way we start this design here is we have to determine, because we're going directly from antenna to the ADD, the way we size up this chain here, the first thing we would do is we look at the ADD and where we want this signal to be sitting at, because you remember it's out of scope of covering here, but the ADD device for these RF sampling devices, it can go up to full scale all the way to the quantization noise. So that's the operating window for these devices. Now, so you start out knowing the signal to noise ratio of the ADD, and then the full scale, you back off with a certain margin, and then you go down to the quantization level, and you try to set this point here at some point somewhere, usually say minus 20 dBm. Usually the full scale signal for this ADD, it basically saturates at around 0 dBm. So if you say operate at minus 30 dBm at this point, that means your signal in here, you know exactly how much gain you need overall in this path here. And it's usually on the order of 40 to 50 dBm. So you're talking minus 60 dBm being picked at this point here by the antenna, okay? Now, so the way to do that, of course, this is I grabbed this and then I scaled it to that chip that I looked at, this chip from analog devices. We start out with the ADD here and the RF front end in here. And we say, okay, the ADD, we have these specs, okay, or we measured it. We have that the waveform that we're dealing with has a 10 dB peak to average ratio. So it can, the amplitude distribution is, the power distribution is between anywhere between 0 to 10 dB of some nominal level. And then the power, full scale power is 0 dBm, okay? And then signal to noise ratio is 55 dBm. So right away, because I picked 0 dBm in here, we know that the quantization noise floor of this ADD is at minus 50 because we have 0 full scale 0 dBm. We go down by the SNR and this level here, okay, which is minus 55 dBm, that's the quantization noise. That's basically the window that this ADD can capture. Beyond that, it can't see anything. So it doesn't do us any good to try to get the received signal to be below that level. So what we're going to do, we're going to go on the other end, which is the thermal noise limit on the antenna. So the thermal noise limit is limited by this much here. It's minus KTB, which is the minus 174 dBm per hertz. This is per hertz. Plus the logarithmic ratio of the bandwidth. Okay, in this case, I took a bandwidth of 100 megahertz, so that's 80 dBs and minus 174. So you end up with this number, minus 94. Now we know that that noise level is going to be increased up by the noise figure. Okay, so because that's noise on top of the thermal noise. So you're going to enhance the noise, the noise floor by that much, which is, in this case, I took an example as noise figure being 4 dB. So that means you're at minus 90 dBm. So now, then your receiver, the function, the way you size this receiver in here is you want this minus 90 dBm in here. You want to bring it up so that it's above the quantization level by some factor. Usually some people say 10 dB, 20 dB. There's a number where you want to bring it up so that you don't degrade the signal to noise ratio by more than 0.1 dB. And I think the number is like 10 dB. But in this case, I said, just to simplify the math, I said, let me try to bring the minus 90 dBm noise floor of my system to 50 dBm, okay, which is 5 dB above the quantization level. So that's basically saying that, then that means my receiver in the front end, okay, plus the 90 dB should equal 50 dB. I'm sorry, the gain here minus 90 dBm equal minus 50 dBm. This is an error. I apologize. So if you calculate that, you know, this is minus, so that means the GRX is going to be 40 dB, of course. So and that's what you usually see on these systems, like this example in here, for instance, on the receive path. You can see that this is they picked up this curve device in here, which is 20 dB, and another curve LNA, which is around 18 dB. So that's 40 dB in here. Okay. All right. So with this now, oh, sorry. So your signal is going to be sitting at this, your noise is going to be sitting at this level. That's the noise level. But now again, now we have SNR requirements. For instance, for the 64 QAM, the signal to noise ratio, we know from tables of modems, the SNR has to be 22 dB at least. Okay. So what that says then, I have to be above the minus 50 by 22 dBs. Okay, which means that my signal has to be sitting at minus 28 dBm minimum. So this now minus 28 dBm at the ADD, that's what's basically where my signal is going to be sitting at if your signal is at the minimum level, okay, which is 22 dBs above the noise background reduced by the noise figure. So now you look at this, minus 28 and the full scale is 0. So that's about 30 dB window. So you're good with that, because your signal can go up by 10 dB and still have a back off 10 dB, more than 10 dB. So you're okay. So with this, this shows the principle of how you size basically this chain in the receive path. And here in the case where you go antennas to ADDs, antenna to bits, some people refer to, in either the FPGA, SoC case, or in this case. And then you start, of course, distributing that. You've got losses, you've got the balun loss, you've got the copper loss throughout, you've got filter losses, and then you've got the switch loss. This switch in here, we utilize it so that when we transmit, we put this switch into 50 ohms, so you're terminating any reflections from the any leaking from the transmitter goes into the 50 ohm instead of going into the LNA, which is sensitive device. You don't want to damage that. So that's what that switch for. So here's some loss, and of course, don't forget the losses in the front end filter and the circular. Okay. All right. So now, if we are sampling, like in this case here at 4 gigasamples per second, and our signals say 3.5 gigahertz, so your signal sits out at 3.5 gigahertz as an example with a bandwidth of 100 megahertz. If you're sampling at 4 gigahertz, that means your Nyquist bandwidth is at fs over 2, which is 2 gigahertz in here. And we see that from the relationship of the mixer-like subsampling. If you're sampling at 4 gigahertz, signal which is 3.5 gigahertz, we end up at a signal which is basically 4 gigahertz minus 3.5 or plus that, which is this, in this case, this one here, which is at 500 megahertz. So meaning in the digital domain, this signal in here is going to be at 500 megahertz. So then you would have to rotate it to baseband to do the decoding and other signal processing, and that can be done with numerical controlled oscillators basically. And these functions are available for you in here in the basically in this here. So I'm sorry, in this path here. So you've got the down conversion digitally here and stages of that, and then you have other various tools as well, okay? So on the transmit path, likewise, we're starting out with a DAC in here. Let's say that we've used the DAC system where the signal is at minus 10 dBm, which is 10 dBs away from full scale of 0 dBm. So we've got a whole chain in here. We need to go with unbalanced to balanced, balanced to unbalanced, okay, or balanced to the single-ended, and to go to the antennas. In this case, for instance, if we go into 40 dBm, if you need to count all these losses and, of course, distribute your gain in here. And that's what I'm going to demo in the next session, in the next video, is a design example where you have to, how do you go, once you, for instance, we know we have to go from 40 to minus 10. So that means the overall gain of this chain is 50 dB, okay? So that means we have to distribute this gain. So we have to go off the shelf, like for instance, in this case, they use this balun from Anarin, bandpass filter from Johansson, and a coupler in here, usually, either printed coupler or off-the-shelf coupler, SMD coupler. And I'm going to show how you distribute this gain and how you optimize this chain. So, but this is how you size up the chain between for the transmit to from the DAC to the antenna, from bits to antennas. Now with giving this chip here, okay, and giving that you have 4 DACs and 4 ADDs, we need to know how you would architect your system. We know that we're gonna do 4 transmitters, 4 receivers, but we can also utilize linearization as well. So like I said, we're giving this system in here. So now we can try to optimize the hardware use with the limited resources of 4 DACs and 4 ADDs. Since we might need some linear power amplifier linearization, we could utilize the system with, say, 2x2, 2 transmitters to receiver, in which case we can utilize one of the receivers for the sole purpose of trying to linearize the power amplifier, like in this case in here, okay? Also, we could utilize, since the signal level is strong signal in here, we decide on how much coupling we need in here, and this is high power, this is a PA. So we could also as well multiplex the use of one of the MIMO receivers themselves as a way to do linearization, since linearizing that PA doesn't have to be all the time on. You basically, if you don't change the dynamics of the signal, if it says the same signal level, same drive level, same temperature, same modulation. So basically you have periodically go in and figure out linearization in here. You linearize this PA and you can set the power level depending on, equalize the output or whatever you need to do for this PA, utilizing methods of loop back, okay? Now, so how do you, the overall architecture for designing a 4 transmit, 4 receive would be like this, okay? We have an FPGA, and we have back here is where we interface to the fiber optic network, to the Ethernet on the gigabit Ethernet on this side, or whatever back end way of reaching out to the network. And then we have this chip that we just used, which has 4 DACs, 4 ADDs. And we have 4 sets of these here. And we can go out and use 4 antennas to implement this system. Now, a common way to implement these for sub-6 GHz is we utilize the plus minus 45 degree polarization on the elements. So we send out, we transmit 4 signals using 4 different polarizations, and you can have them offsetted in frequency, or they can all be at the same frequency. Now that's for you as a system engineer. You can go in and figure out how you're going to do that. Now, I showed it being implemented for two sets of circular or dual polarization antennas. So you can actually get 4 beams out of this, okay, at 4 different information signals or 4 different frequencies within the bandwidth allowed. You can also get this and split it off and go into another multi-antennas. So it doesn't stop right here, really. I mean, in this case, I showed it, it ends at a single antenna, but you could go in also and actually multiplex the signal to go into a panel antenna of, say, 64 of these antennas, okay? So you can utilize, this system can be spatially multiplexing, where you send different information on different polarizations. So you could have this at 1 frequency, this is at 1 frequency. So you have 2 beams in here, you have 2 beams, that's 4 beams total. Every beam is carrying different information. That's 4 times the information level that you can transmit and receive. So that shows, that's what was called 4T4R. Or you could send the same information now, and then on the receive side, you could do that way you increase the signal to noise ratio, so you can do coherent maximum ratio combining on the receive side if you want. You know, there's many ways you can configure this system. Now, this is, so we covered the sub-6 gigahertz architecture for a transceiver for either small pico or CPE or macro base station. And let's go next and cover more so we can show actually the millimeter wave, how we configure that. And like I said from the beginning, this is so we have 2 ways of as you know, that for the this slide here, we showed that we know that for the sub-6 gigahertz band, we don't utilize any frequency translation. So, and that's what we just covered. We showed how with single ADDs and discrete ADDs or SoC ADDs from companies like Xilinx with the RF system on a chip, how you would implement a sub-6 gigahertz transceiver. And the millimeter, which we're going to go next, is basically the only difference, we have a single frequency translation, okay, on top of the sub-6 gigahertz system that is similar to this, okay? So let's stop it right here so we can make the videos shorter, and we'll continue in the next video for millimeter wave transceivers. This is Dr. Mohamed Nezami again. Thank you. I appreciate you. Thank you very much. We'll see you in the next video.